At the outset, let me first thank the organizer. And the session has two combined topics like quantum phase transition and 2D Moire system. So I'm going to talk both of them because it's kind of a session where I can talk both of them. Okay. So what I'm going to talk today is the quantum interactions which we have been looking at in the chalcogenide system in our lab for last 6-7 years. Primarily, I will be talking about charge density wave systems which are unique, and this particular research has researched again for new understanding, and that's what we are going to talk about it. Yeah, so this is the outline of my talk. I'm going to give you some overview of the research work what we are doing at IIT Mandi. Then I will go to the technical part of my talk. To save the time, I'm not going to go to the detail of the outline, but yeah, okay. So this is my group, and so we work on thermoelectric materials and quantum materials. We look at the quantum interactions in the quantum materials where we can have the applicability over the thermoelectricity. So these are the crystals we have been working on. These are the materials where we look for the applicability of these materials. We also work on the functional devices based on these materials. So we work on the flexible thermoelectric generators. We work on the graphene based sensors to find out the applicability in the fluoride sensors and all those. Yeah. Okay, and recently we started working on the multi-body phenomena in 2D materials where we worked on bismuth telluride, bismuth selenide based systems, and recently we also worked on the twisted WSE2. And we do a lot of instrumentation as well. These are the major publications which came up from our group, and the research is funded by various funding agencies. We are thankful to them. All right. So first few slides are for the students. Actually, when we are talking about chalcogenide materials, so we are talking about the chalcogen atoms. When you make a compound with transition metals or the rare earth, you call them as a transition metal chalcogenide materials, and they have very interesting physical properties, starting from semiconductor to metallic to the quantum phase transitions to the charge density wave, superconductivity, spintronics, everything what you think about the physical properties, these materials show that. Yeah. And they make a very good platform for understanding the new science over there. Yeah. And you know that recently a lot of 2D materials using this transition metal and chalcogenides have got a very good interesting structure where you have the metal atom is sandwiched between the chalcogen atoms, and then you have a wonderful gap, and that gives you a lot of interesting property that you can exfoliate it, and then you can go over the ultra atomically thin size. Okay, and then you have the interesting electronic properties. All right, and what happens is when you exfoliate them, okay, their bulk property changes, and you have a very interesting physical properties when you go to the atomically thin layer. So you have a high surface to volume ratio, so they are good for the catalysis for the solar cells. You can look for the electron photon or phonon interactions in these materials because of the confinement effect. They show very interesting optical activity, and they have a very interesting electronic properties as well. So these materials are good when they are extremely thin, close to the atomic level. So what is interesting about the MS2, which is one of the most interesting material, people have started working on it. So what you have it when you exfoliate them. So what you have is when you go from bulk to monolayer, the band structure changes, and it goes from indirect band gap to direct band gap, and that actually gives rise to very interesting photoluminescence properties. So you can see here. So this is the triangular WS2, and when you shine it with the polarized light, you get a very good PL emission from it. And this is coming because of the confinement effect, which is well known to us with the quantum dots. All right. So the light matter interactions gives a lot of interesting properties because, and one of the important technique is the Raman spectroscopy, because you know that it has the photons, it interacts with the atomic vibrations called the phonons, and of course the electronic states are associated with those atoms. So you have the electron, photon and phonon interactions, and the scattered light gives you a lot of information about these materials. Okay, so when we talk about the multi-body quantum interactions in the materials, there are a lot of interactions between the electrons and phonons, and their coupling gives rise to the interesting properties. For example, when you look at the textbook definition for the phonons, you have the acoustic vibrations in the optical branches or the optical vibrations, and they are associated with the band gap. So you don't have an interaction of the optical phonons with the acoustic phonons. But there are materials like some of the minerals, they have a crossover of the acoustic and optical branches, which gives rise to the high scattering of the phonons and leading to a poor thermal conductivity, which is very good for the thermoelectric applications. Then if you look at the anisotropic structures of the materials, you can do the polarized Raman spectroscopy and can find out these interactions also are the anisotropic, and their coupling is extremely anisotropic, and you can enhance them by exfoliating and getting the polarized Raman spectroscopy. Okay. And so this is the second part of my talk. If time permits, I will talk about it. This is the recent paper we are having, but yeah, of course. And as I mentioned that the 2D materials have this MOS2 where you have the photoluminescence which is coming from the excitonic emissions, and you have different excitonic emissions in these materials, and these interactions gives rise to the biexcitons as well as the excitonic states of the excitons. But what I'm going to focus today is the charge density wave in this material. So what is so interesting about charge density wave? So when we talk about charge density wave, it's a very simple phenomena. So you think about a one-dimensional chain of the atoms, okay, and then you have the electronic density. When you map it, what you see is that if you do not have a charge density wave, if you have a one-dimensional chain, you have a band structure like this one. So very simple. Okay, when you go to the low temperature and if you look at the charge density wave, then you have the modulation of the electronic charge density wave. And what you see here is that the electronic density rho is equals to rho 0, which is unperturbed electron density, which is here. But then you have a modulation of the charge density wave, which is associated with the amplitude and then the wave vector and the phase, and this is called the charge density. And this is a low temperature phenomena. Very interesting phenomena. Peirce was trying to explain how the electron phonon interactions can lead to the superconductivity, but instead of going into the superconductivity part, he came up with the idea of charge density wave, and it's a very exciting field to understand it. So what you have is that you have, think about it, you have atoms which are separated by a distance a. Now you have electronic charge density modulation, and then you have a periodicity. So you have one particular part, base is here, another base is here. You have a modulation which is 2a. So now with the Brillouin zone has changed. Okay. So what you have here is that the first Brillouin zone here, the band gap is here. Rather, when you talk about the periodicity has changed, you have a band gap which is within the first Brillouin zone. So now you have a folding of the Brillouin zone, and that leads to a gap, and that gap is called the charge density wave gap. So you have a lot of interesting phenomena in charge density wave materials. So people started thinking about it. Okay, I mean, like if you look at the charge density, what may be the reason for that? Okay, so one of the reason which Peirce had started talking about is you have a Fermi surface nesting. So you have 2 Brillouin zone, and there is a nesting between that which can modulate the charge density. So if you look at the dimensionality versus the Fermi surface nesting, so if you have like two Fermi surfaces in one dimension, which means they are just the line, and then the nesting happens between that. So these are the nesting vectors here. In 2 dimension it is the circle, in 3 dimension it is more complicated actually, but charge density wave is very good if you have a low dimensional materials. Okay. And when you talk about the charge density wave, we are actually talking about the instabilities in the electronic density. Okay, and that electronic instabilities can be understood from the Linhart function, which is the measure of the susceptibility. And when you see that, okay, at a particular wave vector, which we call it as a Q wave vector of the charge density wave, you have extremely large Linhart function here for the 1 dimension. For 2 dimension, it is constant here. And you have the electronic instabilities which are giving rise. Okay, so this is one part. The second part is how do you see these instabilities in the phonon dispersion as well. So what you see here is that you have a energy versus momentum here exactly at the point where you have the Fermi surface nesting or the Q vector. You have a dip in the acoustic phonon dispersion as well, and that actually is associated with the Cohen anomaly. So you have a charge density wave state where you have these anomalies happening. So now you have electronic instabilities and you have a phonon instabilities, okay, and they both are associated with the charge density wave. So together with the electronic modulation as well as the lattice distortion, these two are actually stabilizing the charge density wave. And when you talk about the instabilities in the phonons, how do you define the charge density wave? So you have a commensurate and incommensurate charge density wave, which is defined based on the lattice distortion. So let us think about it. This is the undistorted lattice. which has the periodicity of A, all right. Then you have a modulated structure, and if the modulated structure has a periodicity which is non-integer multiple of A, you call it as a incommensurate charge density wave. If the periodicity of the new structure, we call it a charge density or superlattice structure. If the periodicity is integer multiple of A, you call it as a commensurate charge density wave. So these are the two different ordering which can happen in charge density wave material. All right. So when you are talking about the folding of the Brillouin zone, you may expect that there may be new modes coming up because of the folding. So you can think about it, this is the undistorted lattice, so you have the phonon dispersion here, so you have acoustic phonons, then the optical phonons here, and this is with the typical undistorted lattice. When you distort the lattice and you are actually folding the zones, now some of the modes which are not at q equals to 0, you have the new modes coming up. So that means the charge density wave can have a new modes which are coming up because of the zone folding. So you have collective amplitude modes, phase modes, and as well as the zone folded mode, and I'll tell you like how these modes can be visible. Okay, so now the question comes actually, okay, what is the reason? The reason what Pearls gave it over the charge density wave because of the reconstruction of the lattice and Fermi surface nesting, or it is the electron phonon interactions or collective excitations, or it may be the electron correlations. All right, and if you ask me, how do you see that there is a charge density wave transitions? So one of the ways, because in electronic instabilities are associated, so you do the transport measurements. So people have done the transport measurement, it's rho versus T, and then you see the transitions. Okay, these transitions can be the structural transition as well or the ordering transition as well. Okay, but there are some reasons that okay, these transitions are called the charge density wave transitions. You can see from the transport measurement. The alternate way is actually look at the imaging or the structural understanding. So you cool down the material at low temperature in the charge density wave and do either the TM imaging or do the X-ray analysis. You will get some superstructures which are coming up in the CDW phase, which are associated with these instabilities. We look at it in a very simple way of Raman spectra. So you know that when you do the Raman spectra, it is essential to have the polarization. Okay, so you need to have a material which is polarized, and of course it is associated with the phonons as well. So you can get a direct evidence of the charge density. Okay, so we started looking at it from the VSE2. So this is very old story, but we came up with the idea that okay, it is not the Fermi surface nesting, it is the electron phonon coupling which is driving the charge density wave in these materials. So when you do the Raman spectroscopy of any of the DMDs, so you get these modes called the asymmetry modes or the EG symmetry modes. Okay, these are associated with the atomic vibrations. So asymmetric modes are the out of plane vibrations, and this is the in plane vibrations, and then you have a 2pH mode, which I'm going to talk in next few slides. So this is the VSE2. So this is at 300 Kelvin, which is known CDW state. Then you have a 10 Kelvin, which is the CDW state, and then you have new modes which are coming up here. And if you do the temperature dependent Raman, what you see here is that right at 100 Kelvin, which is the CDW temperature for the VSE2, you start getting a new mode which are appearing here. And then when you go to the 40 Kelvin, you start getting another Raman mode here. So now these two Raman modes are associated with the charge density. We call them as a charge density wave super modes. Yeah. All right. And that thermal dynamics actually tells you a lot of the information about those materials. So you look at here, this is the transport of the VSE2. So you have a resistance versus temperature. So you have around 105, there is an incommensurate charge density wave. Then it goes again, and then you have a commensurate charge density wave. So how do you understand whether it is a commensurate charge density wave or incommensurate charge density wave? So when you talk about low temperature commensurate charge density wave, which is coming up here, so which means you have a new ordering which is coming up in this material. So how do we understand it? So we plot the integrated intensity of the Raman modes as a function of temperature. So what you see here is that around 105, the instability starts, and right at the 40 Kelvin it goes down. So which means there is a new ordering which is coming up in this material. So this was the first evidence or the first explanation we gave it over these materials. Yeah. So the take home message here is that if you have this kind of behavior of the integrated Raman intensity, you say that okay, there is an ordering coming up in these materials. Yeah. Okay, and then we started looking for new materials or the materials which have more charge density of materials. So the classic materials are the 2H NbSe2 and the tantalum sulfide. And you can see again at room temperature these materials have the EG mode, AG mode, and of course the 2pH mode is coming up. Now look at the transport. So tantalum sulfide has a incommensurate charge density at 76 Kelvin, while for the NbSe2 it is 30 Kelvin. Now NbSe2 is superconducting as well. So now there is a competition between the charge density wave and the superconductivity. That brings the charge density wave transition to lower temperature. Since the charge density wave, the superconductivity in tantalum sulfide is even less than 1 Kelvin or something, so you still have a. So these are the good materials to look at it. Okay. So we started looking at it. So now this is the electronic bend structures, which shows that what kind of the bends which are forming the Fermi surface of these two materials. I'm not going to go into the details, but what you can see here is that these are the modes. Okay, so this is in the electronic instabilities which we wanted to show is that, okay, Q1 and Q2 where you have the instabilities because these are the negative frequencies here. Alright, so I talked about the two phonon mode in the tantalum sulfide and NbSe2. It was existing in VSE2 as well. Okay, here. Now this is the phonon dispersion, phonon density of states versus frequency. So I want you to focus here. It is at nearly around 155 centimeter inverse to nearly like 230 centimeter inverse. You see that there is no phonon density of states, which means we should not get any Raman mode here. But if you look at, so this is for the tantalum sulfide, this is here, this is around 160 to 220 or something. This is the mode where it is coming. Okay, so what is this mode? Experimentally, I see there is a mode, but when I do the theory, I see no phonon density of states here. So now this is very interesting. Okay, so this is an optical mode which is observed experimentally, but it is coming because of the interaction of two acoustic modes and leading to a single phonon mode. That's what we concluded here. All right, and so now this mode, 2pH mode, is coming exactly at double the frequency of the common anomaly, and we started looking at it. What may be the reason? So what you have here is that when you talk about the interaction of the two phonons, you get a matrix. That matrix actually lead to two acoustic modes which are not excited by the Raman, okay, but when they interact, they can lead to an optical mode which is observed in the Raman spectra here. Okay, I'll not go into the details here, but what we did actually, we looked at the symmetry of these modes, okay, and we found out that this particular mode had the vibrations both in plane as well as out of plane vibrations based on the polarized Raman spectroscopy. And that actually gave us the idea that, okay, this is a completely new understanding which we understood from the Raman spectra of these materials. All right, so this is the vibration of, so you know that when you talk about asymmetry, you talk about only the out of plane. When you talk about the e-symmetry, you talk about the in plane modes. But here in this particular mode, we have both the symmetries existing, okay, and that is coming because of the interactions what you have it from the acoustic vibrations. All right, and how do we understand it? So we understand it from the temperature dependent Raman spectra, and so what you can do is that from the temperature dependent Raman spectra, you can estimate from the enharmonic model that if this is following, the red curve is following the data, that means it is a harmonic behavior, okay, and if there is a deviation from that, that actually gives us to, there are some interactions, and we call that the electron phonon interactions, which are leading to the instabilities in these materials, and that is happening exactly at the charge density wave transitions. And of course, here we can see that the in-plane modes, which are the EG modes, are actually more sensitive towards the formation of the CDW superlattices. So very simple technique can actually gives you idea about the charge density wave in these materials. All right, and of course, we estimated the electron phonon coupling constant as well as the enharmonicity in these materials. I'll go back, yeah. So what you can see here is that there is an enharmonic term in the fitting here, and there is an electron phonon coupling term, and these two terms, you can see that NbSe2 has a lower electron phonon coupling but higher enharmonicity, while the tantalum sulfide has a higher electron phonon coupling term and the lower enharmonicity, and that actually gave us the idea that, okay, if we thin it down, what will happen to it? So we started, of course, we got some zone folded mode as well. So I'm not going to go into the details of the zone folded mode because these are the modes which are coming from the chart density wave, and we call them as a chart density wave super modes. Okay. So what happens if I thin it down? So you go from bulk to couple of layers, and then you go to the mono layer. So instead of going into the number of layers, we started thinking about taking it into the unit cell, because 2H tantalum sulfide, which means 2 monolayers are required to make 1 unit cell, right? And it's very difficult to get the monolayer of these materials. So we started, because this material has a higher chart density wave transitions, so it's good to do the measurements. You don't need to worry about going to the low temperature. We expected that if I thin it down, I might get CDW transition at lower temperature. This is what you think about it. So we exfoliated it, okay, and then we looked at it. I'm not going to detail, okay. So there is a debate going on. If you have a monolayer of tantalum sulfide, some people say that, okay, you will lose the CDW. Some people say that, okay, you may enhance the CDW as well. And it's very difficult to conclude from the literature, okay, especially for the monolayer of tantalum sulfide. Now, what we have understood that if you look at the exfoliation, okay, so if you have number of layers which are even number or odd numbers, you have a different symmetry. All right, and how does it work? So if you exfoliate it, you get monolayer, okay, which is non-centrosymmetric. Bilayer, which is because the center of inversion is here, so you have a centrosymmetric, you have a trilayer which is non-centrosymmetric. So you are changing the symmetry, and now this change in symmetry can lead to a new modes in these materials as well. So we exfoliated it, and then we looked at it, okay. So we also looked at from the theory perspective. So what we have done, we asked our collaborator actually do the calculation as a function of the smearing parameter. So smearing parameter actually tells you about the electron temperature, okay, and it doesn't give you the absolute value, but it gives you the range of the temperature where the instabilities can exist. So now you see here the bulk. You have negative frequencies, which means you have a lot of instabilities in these materials. So it's a chart density wave material here. So it's bulk, you have instabilities. But when you go from bilayer to monolayer, what you see is that at room temperature, the black color is bulk, which means no instability is there, the structure is stable. But when you go to the unit cell, or we can say it is a bilayer, you have the instabilities, and you, so even at room temperature you can have the instabilities in these materials. How do we see that? Yeah, come on, move it. Yeah. So what we have done is we looked at the materials with the different thicknesses. So you see this is 300 Kelvin known chart density wave here. So it's bulk 10 nanometer, 7 nanometer, and 3 nanometer. 3 nanometer I took it because it's a bilayer and it's a single unit cell. And if you look at the 10K data, you have new modes are coming up, M1, M2, and M3. These are the new modes which are coming because of the chart density wave. And we looked at the thermal response of these Raman modes. So this is the bulk. This is 27 nanometer, this is 16, this is 10 nanometer, 7 nanometer, 3 nanometer. You see that these chart density wave modes are actually enhanced if you have 3 nanometer, and they slowly work away. Okay, so the bulk and 27 nanometer thick flake do not have a new CDW modes which we were talking about throughout the temperature, but it exists. So now you have two parameters, low temperature as well as the low dimension as well. And we looked at the Fano resonance as well, and the Fano actually tells you what is the electron Fano coupling strength in these materials. Then the deviation again tells you that, okay, you have involvement of the electron Fano coupling. This is very standard understanding from the Raman, okay. And so we look at these modes to estimate the incommensurate chart density wave transitions. So here I'll just tell about, okay, how much time I have?
Another 3 minutes.
Another 3 minutes, so this is okay. So, okay, so what we have done, looking at the thermal behavior of these modes, we identified that there are different regions where you have the chart density wave. And what you can see here is that this is thickness versus the transition temperature. So even for very low thickness flakes, you have a higher T as CW. So which means we concluded that, okay, the chart density wave can exist even at low dimension. Not only that, but it goes to the higher temperature as well. So this is one of the interesting aspect of the area. Okay, with that, I thank the group members and the funding agency. If you have any questions, I'll be happy to answer it.
You can take a couple of questions. We have still about 4 minutes. Any questions?
Nice after nice talk, sir. Thank you. Sir, I have a question that you said that resistance versus temperature can give a signature of charge density wave.
Yes,
What is that?
that's what people do first.
But how the charge density wave creation going to affect resistance in what sense?
Okay, so if you see the data, you will see a slight change in the slope of the resistance curve. Okay.
I see a small kink around.
Yes.
How that is connected to the charge density wave formation?
Okay, so that's what I mentioned in the slide, that the kink is not always the charge density wave. It comes from the structural transitions. It comes from the electronic correlations. It comes from the magnetics correlation as well. Okay, but these are the materials which are standard charge density wave materials. So that's how actually you understand that the kink is coming because of the charge density wave, because there are no other transition associated with these materials.
Okay, sir. I have another question. Second question. You just said that electron phonon coupling strength is known by Fano resonance.
Yes. Yeah.
Like how?
Okay. So okay. Normally, when you have a Raman peak, you fit it with the Lorentzian void function. Okay.
Right.
But when you fit it, you don't get the right fitting. So you need to adopt new models. Okay. And one of the model is the BKT model actually. Okay, where the Fano is involved there. So when you fit it with the known Lorentzian function, which is the Fano function, and there you, from the fitting, you calculate the electron phonon coupling. That involves the electron phonon coupling inherently.
Is there some numbers coming out of
Yes,
the fitting
yes,
that will
yes.
verify the strength?
Yes.
So number will increase and strength will.
Yes.
Thank you.
Any more further question? Anyone? Yeah. So you also actually grew up with
So still you not reach all the samples are HBN encapsulated?
No. These are just the area. Yeah.
And still you not reach one monolayer in the chart.
No, it's very difficult to get it. You need a lot of expertise actually.
Right.
You were asking something.
I think you can continue discussion with him, so we can close now for this.
Yeah, thank you very
talk.
much.
So we'll move forward to our next talk. Thanks.